Hello, welcome to my talk all about the fruits. This talk is about why the commercial planes fly at a high altitude. Many of us have experience flying with the commercial flights, and you may frequently notice the plane cruising at a high altitude of about 40,000 feet or 12,000 meters above the Earth's surface. Then you may ask a question, why the commercial planes fly at a high altitude? And if you Google it, you may be told this is an optimal result for saving fuel consumption because in that height, the air density is much less than the density at sea level, about 25%. And in this regard, it seems the higher the flight altitude, the better. Is this true? If so, why there are service ceilings for all commercial planes? In this talk, I will show the scientific facts why the planes have to fly high. The pictures are the Airbus A380 and the Boeing 787, the Super Jumbo and the Dreamliner. Both are the relatively new types of the commercial plane in Airbus and the Boeing families. In the table, the flight facts about the Airbus planes, Boeing planes, and the Concorde are given for a reference. From the table, it can be seen that almost all commercial planes have a cruising speed at a Mach number of about 0.8 and a cruising altitude 11,000 meters to 12,000 meters. One exception is the Concorde, the supersonic commercial plane with a cruising speed of Mach number of 2.0 and a cruising altitude about 18,000 meters. Relatively, the new models of the commercial planes have a slightly higher cruising speed at 0.85 Mach number, larger than the old models. For instance, A320 and Boeing 737, the best sellers for both companies. So, we might have questions why these parameters are chosen and what are the scientific basis for these facts. If you Google it, why aeroplanes fly at a high altitude, you might get a lot of answers for that. Following are some of them. A higher altitude, a lower air density, thus a lower drag force acting on the plane, so that the commercial airplanes could keep going with burning less fuel. That's why a higher altitude, now around 40,000 feet or 12,000 meters, is referred to as a cruising altitude. In this regard, the higher the flight altitude, the better. However, you will not be told the exact cruising altitude, since this may change accordingly from the different nodes for the planes. That's another reason why the commercial planes fly at an altitude of around 12 kilometers. This is the height acting as a safety cushion and gives the pilots some time to fix things or to return to airport or even to some safe places, even in river, if things goes wrong. Again, in this regard, the higher the flight altitude, the better. More reasons for the high altitude flight. The planes fly in the lower boundary of the stratosphere, an isothermal layer of low temperature, minus 56.5 degrees Celsius. Thus, much less turbulence there. Also, the cool air is good for the engine efficiency. A high flying means that the aircraft are able to avoid other airborne traffic, such as the low-flying light aircraft or helicopter, as well as those insects and birds. And this high altitude will satisfy the regulations from the aviation authorities. For instance, CAA, the UK Civil Aviation Authority, requires that the flight must be over 1,000 feet when over a built-up area, or 500 feet over any person, vehicle, or structure. Also, there are noise issues for flying. The higher the flying, the less noise came down to the earth. It seems all the facts above supporting the higher the flight altitude, the better, and some very good reasons, the red item above. If this is true, then why there are service ceilings for all the commercial planes? In this slide, a simple flying principle of the airplane is shown. In a cruising state, the plane is subject to four forces: the gravitational force, mg, and it reduces during the flight because of the fuel consumption. The lift is the lifting force mainly produced by the wings of the airplanes to cancel the airplane weight so that the plane can fly in the air. The lift is proportional to the speed squared. The drag, since the airplane must fly through the air, hence there will be a drag acting on the airplane. Generally, it is proportional to the air density and the speed squared. The thrust is the force that the engines provide to push the airplane forward. In the cruising state, the engine's thrust must equal to the drag. In climbing, the lift must be larger than the weight mg, and to decline, the lift must be smaller than the weight. To accelerate, the thrust must be larger than the drag, and to slow down, the thrust smaller than the drag. For a commercial plane, its lift and drag can be generally calculated using the following formulas as this. It can be seen that both the lift and drag are proportional to the air density, to the velocity squared, and to the reference areas, AW and F. These are dependent on how the lift and drag coefficient defined, and these areas cannot be changed once the plane is fully optimized. CD is the drag coefficient, which is mainly depend on the Reynolds number and the Mach number in flying. Take an example drag coefficient of a streamlined body in the plot as a reference. When the Reynolds number are large enough, the drag coefficient would become independent of the Reynolds number, for instance, higher than a million or tens of millions. The lift coefficient CL has a similar feature as that of the drag. The important factors here are that both drag and the lift are proportional to the air density and the speed squared. An limitation for the flying speed is the Mach number for those subsonic commercial planes. The Mach number is calculated as the ratio of the flight speed divided by the speed of the sound. For an optimized airplane, the drag is a constant for the small Mach number until the critical Mach number, MCR, which is very close to the Mach number of the drag divergence, MDD. A Mach number, the drag coefficient, would increase very quickly since it is approaching the sound barrier. After the Mach number of drag divergence, the drag coefficient could reach the maximum at the Mach number about 1.0, at which the sonic boom happens since the strong shock wave, as we see in the plot. Because of the drag divergence. So, for the well-optimized subsonic planes, the critical Mach number is chosen at 0.85. These are the cruising Mach number for the Airbus A380 and the Boeing 787. The commercial planes mostly fly in the lower boundary of the stratosphere, between 11 and 20 kilometers above the Earth's surface. This is the isothermal layer, a layer with a low constant temperature, minus 56.5 degrees Celsius. Because of the constant temperature, there would be much less air turbulence for flights at that altitude. The air density in the isothermal layer is between 0.6 kg per meter cubed and 0.1 kg per meter cubed, which is between 49% and 8% of the air density at the sea level. The speed of the sound is a constant in that layer of the atmosphere at about 87% of the speed of the sound at the sea level, 295 meters per second compared to 340 meters per second. And the air viscosity is a constant at about 80% of the air viscosity at sea level. It should be noted that the speed of the sound and the viscosity are only dependent on the air temperature. From the formula of the Reynolds number here, the Reynolds number Re is proportional to the air density, the air speed, and the characteristic length, which can be taken as the diameter of the plane's fuselage. For instance, the Boeing 737 and the Airbus A320, both diameters are slightly larger than 4 meters. and reverse proportional to the air viscosity coefficient. Based on the data from the U.S. standard atmosphere, the Reynolds numbers at the altitudes of 11, 12, and 13 kilometers would be 33%, 28%, and 24% to the Reynolds number at sea level. RE0 would be 8 million at sea level if the Mach number is taken as 0.85 and the characteristic length is taken 4 meters. For such a range of the Reynolds number, the drag and the lift coefficient would be constant, not changing with the different Reynolds number. In high altitude, the air density is reduced. At the altitudes of 11, 12, and 13 kilometers, the air density is 30%, 26%, and 22% when compared to the air density at sea level. Obviously, such a reduction in the air density would cause the corresponding reductions of both the lift and the drag, since they both are proportional to the air density. Thus, there is a conflict here. The higher the flight altitude, the drag would be smaller. This is very good for reducing the fuel consumption. However, for flying, it needs a large lift to cancel the weight of the plane. If other parameters cannot be changed, this is quite true for the optimized plane, then an appropriate large air density would be needed for creating a large lift. Therefore, for the lift, the lower the flight altitude, the better. From the lift formula, it can be seen that how we can generate a large lift to cancel the weight of the plane. We could increase the lift coefficient by increasing the angle of attack. However, this will also increase the drag more, since this change would move away from the maximize the ratio of the lift air of the drag D, or increase the speed of the airplane, but this will increase the drag accordingly, and this might move close to the Mach number of the drag divergence, so that the drag coefficient would be greatly increased. The best solution would be to increase the air density by lowering the cruising altitude, and of course, the drag would increase accordingly. However, this option would maintain the optimized condition for the plane. Therefore, we can conclude now that it is not true. The higher the flight altitude, the better. Therefore, this is why most commercial planes have the compromised flight altitude at about 12,000 meters. In this slide, we examine a situation when a plane has a 10% more weight for a flight, and to see how much more fuel is needed for the situation. The plane is assumed to be designed to have a standard cruising speed of 0.8 Mach number, that is 903 kilometers per hour, at the cruising altitude of 12,000 meters, and the fuel consumption is assumed linearly proportional to the drag of the plane. In the analysis, to support the flight, the lift must be same as the plane weight. Thus, a 10% increase in the weight will cause 10% increase in the lift, as this. So to increase 10% in lift, we can generate this by increasing the air density by 10%, while keep all other parameters unchanged for lift. Based on the data from the US standard atmosphere, the air density at the altitude of 12,000 meters is 0.3119 kg per meter cubed. Increased by 10% would be 0.3431 kg per meter cubed. The corresponding altitude would be 11,410 meters. From the drag formula, it can be seen that the drag would be increased by 10% since it is proportional to the air density. We can see there will be 10% increase in the fuel because the fuel consumption is assumed to be linearly proportional to the drag. A similar relation can be found in the example as this one, the relation of the fuel consumption and the load. In this talk, we have shown the main factors for deciding the parameter for a commercial plane, the cruising speed and the cruising altitude. However, it must be stressed, the optimization of all the parameters would be a very complicated process.